So problem number 685, random connection tree. So in this problem, what we are given one tree, which is a directed graph. Okay, actually, like initially it was a tree, but now some extra node has been added to it, or some extra edge has been added to it. So now it become a graph. So this says that a rooted tree was there, which is a directed graph, such that there is exactly one root node for which all other nodes are descendant. Plus, every node has exactly one parent. So what they are saying that every node has one parent except for the root node which has no parent, right? So that is what this question is saying. The given good directed graph. So here they are saying it's a directed graph. As we can see, it's a graph, but originally like it was a tree, and one extra edge has been added, which has transformed this tree to a graph. Like if you see here, if you like remove this 2 comma 3, then what will be remaining? This and this only. So we can see that this was a tree, but if create one edge from 2 to 3, then it become a graph. So now they are asking to remove that resulting edge from that particular graph, so it again become a tree. So let's understand this problem, what it's saying. So before moving to this problem, random connection, to first understand one concept called DSU, disjoint set. So, and how this concept came into. So let's forget the question for a moment. Let's suppose we are given some nodes. Here is one node, and it's been attached to 2, and here is another node, 2 is attached to 3, and here is another node, 4, which is attached to 5, right? And somebody asks us that we need to find whether 2 is connected to 1 or not. 2 is connected to 1 or not. Somebody asks us. So as who has done graph, then they can simply say that okay, we will run like BFS and DFS, and we will find whether 2 is connected to 1 or not. Similarly, if somebody tells us that whether 2 and 3 are connected, then again we will again run DFS and BFS to find the same, right? And suppose like this, there are n number of queries or questions that been asked to us. Then for each such queries, we need to run DFS and BFS every time. And that will be not very optimal, right? Because we need to run n number of times, and n can be very large, right? So instead, what we can do here, if suppose something was there like this, like suppose we have something like this A, and A contain 1, 2, and 3. These are basically these nodes only, 1, 1, 2, and 3. And we have B, which contain basically A and B are the leader. So if we say we have one leader A, which contain node 1, 2, and 3, and which B, which contain all other nodes, right? So now if someone says to us that whether 2 and 3 are connected, then we can say that if their leader are same, then they are connected, right? And similarly for 1, 2, 1, 3 also, because their leader are same leader, so they are connected to one another. And similarly for 4 and 5, their leader are same, so they are also connected, right? Now suppose in the previous approach only, if we make one as a leader for this group, so one is leader for 1, one is the leader for 2, and one is the leader for 3. And similarly here, if we make 4 as a leader for 4, and 4 as a leader for 5 also, right? Then what we can say is, if again their leader are same, so they belong to the same group. So this idea give birth, and this concept give birth to the idea of DSU here. and this leader is called ultimate parent in DSU. Ultimate parent UP. I can write it down. Now suppose if somebody asks us that we need to find whether 2 and 3 are connected, then what we can do, we can check whether their leader or ultimate parent is equal, right? If we can find the ultimate parent of 2 and we can find the ultimate parent of 3, and if they are equal, then it means they are connected. Now suppose here one more observation came. As we can see, now suppose we are given the same array what is given here. We've taken the same edges in this part. So what we got, we get something like 1 comma 2, and second they have given 1 comma 3 and 2 comma 3, 1 comma 3 and 2 comma 3, right? So in this question we are given directed graph, sorry, but let's suppose for a moment this is a directed graph. Let's suppose for a moment this is undirected graph. Undirected graph. Okay. Now suppose we connect these edges. We connect 1 to 2 and we connect 1 to 3. So we can see the ultimate parent of 2 became 1 and ultimate parent of 3 became 1. Now if we connect 2 to 3, so we can see the cycle is there, right? And conditions are both when this point came, so we can see if their ultimate parent are same, it means if their ultimate parent are same, then they will form a cycle in case of undirected graph. But now suppose in this question they have given directed graph. Now let's again draw the same diagram. 1 is connected to 2 here, and here 1 is connected to 3. Now we can see still the ultimate parent of 2 is 1 here and ultimate parent of 3 is also 1. But if we see now the last is 2 to 3. Now we can see though the ultimate parent of 2 and 3 are same, but still we do not see a cycle, right? It's not a cycle. It's coming here and it's coming here, right? But here in the directed graph we can see the cycle if their ultimate parent are same. So we can say that if ultimate parent are same, then we can't deduce that whether a cycle is present or not, or whether they belong to the same component in case of directed graph. Now in case of undirected graph of we can say that if ultimate parents are same, then cycle is there, and if we remove that edge whose parents are same, then we will form a tree, right, in case of undirected graph. But as we have just discussed, in case of directed graph, like even if ultimate parent are same, it's not sure whether they are like whether a cycle is there or not. So what we can check here, if we see closely, one thing we can observe here, that this 3 has 2 parent. One is this parent and another is this parent, right? But if we see the question is saying that exactly one node for which all the nodes are descendant of this node, thus every node has exactly one parent except for the root node which has no parent, right? So here 3 has, but so this is forming one extra connection for us. But how we will check this, right? So here from here we can deduce either 1 to 3 is forming one extra edge, or 2 to 3 is forming one extra edge. So now if somehow we can find these 2 parents, then we can find these edges also, right? And we can find which one to remove also after that. but our first main aim is to find this edges, these two edges, and for that we need to find these two parents. And also it is pretty sure that only one node will have such type of condition in our question, right? Only one node will have two parents, and that two parent will be responsible for forming one extra edge, and we don't know which is responsible, like either 1 to 3 or 2 to 3. So what we will do, so now we are sure that the DSU concept of saying that if both nodes have the same parent, then cycle exists, right? This is not correct here in case of directed graph, as it was totally correct in case of undirected graph. We can safely say that if two nodes has the same parent, then cycle exists, and we can safely remove that particular node from here. So what we will do to find these two nodes, we will take one array array will be of n plus 1, since it's like 0 indexing, and so 1 2 3. So 1 will have the parent of 1, 2 will store the parent of 2, and 3 will store the parent of 3. So we go query by query here, whatever is 1 2 1 3 and 2 3. So first will be 1 2 2, so it means 2 have a parent of 1, so it means 2 have a parent of parent 1, and second given 1 2 1 3, so it means that 3 have a parent 1, and our second was 2 to 3. Now 2 to 3. Now when we will reach 3, we saw that it's not 0, right? If no parent is there, then it will be 0, right? But if we come here, we saw that it's not 0. It's not equal to 0, that particular box. So we can say that it already has one parent stored in it, and this 2 will be another parent for it. Like so, write this. We will find the node. Node will be 3, and 2 parents which it have. So 2 parents are here 1 and 2. So what is the, I mean, if we write the logic here, so if we can check if that parent index not equal to 0, it means that is already been visited before and some parent is already have, and here we can find the 2 parents. Now since we have found the 2 parents, and we can also safely say that 1 is connected to 3 and 2 is also connected to 3, so we need to remove any one of these to make our graph a tree. Now what we will do, we will run our DSU operation here. By skipping any of these, either we can skip 1 3 or we can skip 2 3 by right. So by DSU operation I means union by rank, or union. We will do now union by rank simply means, let's suppose we have 2 trees here. I will give you a small example. 1 2, and here is 3 and 4. This is 1 tree. So the rank of this graph is equivalent to 3 approximate, I mean the height, approximate height. And we have another graph here, suppose 5 attached to 6, and so the rank of this will be, and rank is always calculated from the ultimate parent. So we can see that this is the ultimate parent or the leader, because for 4 also this is the parent, and for 3 this is the parent. So ultimately for 4 1 will be the ultimate parent, and for similarly for 2 also 1 will be the ultimate parent, right? And for 5 also the parent itself is the ultimate parent, right? So rank is always correlated with the ultimate parent. So here if we see the rank of this graph is 1 and the rank of this graph is almost equivalent to 2. So if we union this both graph, then what we will do, always we will attach the smaller graph under the larger graph. See what I'm saying? If we attach this graph to this graph, so it will be attached something like this. So suppose we are doing the union by rank of these two, like any of nodes, right? So what we will do, suppose we need to do union by rank of 2 and 6 here. So union by rank will be always be done on ultimate parent, right? First we will find the ultimate parent of 2, we will find the ultimate parent of 6, ultimate parent of 2 we will find, which will give us 1, as you can see, and we will find the ultimate parent of 6 here, which will give us 5. Now we will find the rank of both, rank of 1, which will be approximately, if we can see, will be something like 3, and secondly we will find the rank of 5, which will something approximately will give us 2. So we will, there is a concept, we will always attach smaller rank under the larger rank. So, and we will always attach the ultimate parent. What I am trying to say, suppose this is the same graph. If we take 1, 2 and 3 is there and 5 is there, sorry, 4 is there and 5 is there, 6 is there, and we are doing union of 2 comma 6. So we have find the ultimate parent 1, ultimate parent 6, 5. We have find their rank. This rank is 3, this rank is 2, and we will try to attach the smaller rank under the higher rank with their ultimate parent. So how it will get attached? It will get attached something like this. This is 4, and from here it will get attached. So we can see the rank remains same, right? The rank did not increases for the 1. Only we have changed the ultimate parent of 5 to 1 now. So we can reduce that. If ranks are unequal, then we will just change the, if ranks are unequal, then we will just change the ultimate parent. Now suppose in case of ranks are equal, like suppose here we have one something like this, and here we have another graph, and if we want to do the union of 3 comma 5 here, so again the same step, we will find the ultimate parent of 3, so it will be 1, and ultimate parent of 5, which will be 4. We will find the corresponding rank, so the corresponding rank will be 2 here also, and for 4 also it will be 2. So we can see both are equal, right? So in this case, if we try to attach, like here we can 1 to 4 or also from 4 to 1. So suppose if we attach 4 to 1, so it will become 2, 3. Now if we try to like attach 4 to 1, so we will see that 4 will be here something like this, and this will be 5, and this will be 6. So we can see that the rank increases in this case of this equal rank, the rank increases. So this is a simple short form like union by rank. Yes, so now move to our previous question, what we were doing. So we have already found the 2 parents and the corresponding edges. So 2 parents were 1, 2, 3 and 2, and it's like edges for 2, 2 to 3, right? Now we are not sure which one to remove so that our graph will become a tree. So we will try both of them one by one. So like our original question, if we see here, was 1 2 1 3 and 2 3. 1 2 1 3 and 2 3, right? So what we will do first, like in first case, we will iterate it one by one, and if 1 comma 3 come, we will skip this part. We will not take this part, we will skip this. And if the DSU operation give us the cycle, it means since we have skipped 1 comma 3 and still we have gotten the cycle, so it means 2 comma 3 was our extra node, right? Like this we can find this. Like we are just skipping any of one, like suppose we skip 1 comma 3 and still we found the cycle, then it means 2 comma 3 is our extra node. And if we didn't found the cycle by skipping 1 comma 3, that means 1 comma 3 itself was the edge that is forming a cycle. So if we get back to the code here, we are just creating one ultimate parent and one rank array. We are initializing it, and here we are finding the ultimate parent with the help of the recursion. This is simply path compression that we are doing, and here we are doing union by rank, as I've told before. Like if rank of A is greater than rank of B, then we are moving smaller under larger. So suppose here UPA is larger, so B will attach itself to A here, and similarly here opposite. And if here both ranks are equal, then we are just adding this, we are like attaching any of B or A, and we are just adding up the rank. And now the main code. So the first part of our code was finding the extra edge. So we have taken 2, so there will be 2 extra edges, and we have 1 2 2 and 1 2 3, and we are finding the extra edge. So as we have told, if that particular like index is not 0, it means it has been listed before. So there is the condition where we will find the extra edge. And now here we are just iterating our main array edges. Now what, as we have told, we have found 2 extra edge 1, extra edge 2. So we will skip any of that extra edge. Suppose we have skip the second edge. Now we will try to find if still cycle exists or not by skipping extra edge 2. And if still the cycle like exists by skipping the extra edge, then it means the other edge, which is extra edge 1, is the edge that we need to like return, that is causing our T2 node. And at the end we are just combining 2 nodes given we are just doing the union. And suppose if our loop end and we didn't find any cycle by skipping extra h2, it means extra x2 itself was our answer.